where you published this work recently, and you can see that that is related to both like thickness as well as like frequency. Because with frequency you have lesser penetration, so you see lesser differences in the time of arrival. So that's some of our preliminary results, and also kind of we created a model that follows the same kind of. So I'm not go into this, but they have gave us the same prediction. But it really helps when you have a model that kind of predicts the same kind of nature that experiments will go. This is my last slide on eddy current, which is where we have been able to take it and actually put it in a in a real laser system. The laser doesn't move here, so it's static. But we are working on like actual moving lasers as well. This is a very complex laser system that we don't not want to go into. At the end of the day, the laser shines on the metal part, on this metal plate, and you can see this is the eddy current carrier that is positioned below the metal. To make some real temperature measurements, we also place a few thermocouples on the plate to measure what the real temperature is. And you can see that we use two different laser same power level but for a different duration. One for 1 second, so it should deliver more heat, and one for zero point 0.5 seconds lesser heat. So you can see a similar response. As the laser heats the spot, then the current signal changes, and then again it comes back to the residual state. So all in all, it's a work in progress, but we've been able to show that eddy currents can be used to detect subsurface heat propagating within metals, and it can be potentially used to detect heat in like thick metals as well. And it provides something more than what thermal cameras do, which is important. Like for example, thermal hotspots may lead to residual stress in the future. And so can we use this, for example, in welding, where like even in conventional welded parts, look at temperature profiling during welding process, and go from there. So how do you say really deep inside? How do I say that? We've been able to like experimentally see at least upwards into. Yeah, it's not less. Like in context, what is the low frequency? Close to a kilohertz. Not super low, but close to a kilohertz. Uh, and then we've been also looking at actually placing the array from the top. Because that's a question that we keep getting is how do you kind of have sensitivity to pass? Your location will be challenging. Even if you go to frequency, you will not centimeter. Yeah. Whatever you are getting is an average of whole of 1 centimeter. Yes. Like, within that 1 centimeter, where exactly is your hotspot you can write? You cannot. That is the inherent resolution. Not resolution, it's space for it to be physical and to be able to read them. So we're working on basically a GMR array sensor that can be placed like really close, but still gives us like about few millimeter resolutions. Yeah. All right. Changing gears. I have less time, so I'm going to be uh, moving fast. This is a different additive manufacturing system. So the second additive process. This is called metal jetting. A nozzle that deposits liquid metal onto a part, as I was showing in one of those cases. This is an actual video, so you can see um, this is a nozzle, the droplet falling. So very high resolution video of the droplet falling. The goal is not to understand what's been printed, but the goal is to track this droplet while it falls from the nozzle to the film plate. And why that is important is because of this. It's because all the process parameters like pressure, inert gas environments, just experimental uncertainty, whatnot. All of those kind of affect the size or the shape of the droplet that's falling from the nozzle. And so it's really important to have a good grasp. It's really important to have these guys than these ones falling from the nozzle. And so we really needed to, at this point, this is a high-speed camera that was trying to track the droplets, but we wanted to replace this with a sensor that can give not a gigabyte of data for every droplet, but just enough information that tells us what that droplet is going to be. So that's where we looked at millimeter waves, like millimeter wave technology, and we almost use it as a radar. So I'm going to say how we use it. And we had two different diagnostics for it. One where we made it super complicated, then we realized it's not feasible, and then we made it simple. So this is actually our first take at it. Maybe what we call as a power divider or T-junction. This is very known in the microwave community, where you have an input port and the power gets spread to two different ports. These the input and these two different ports. And it's typically used as a power divider, but what we use, we cut the two halves and then we let the droplet actually fall through this section. And what happens is typically in a balanced case, you would have even power distribution. But when the droplet is falling through that part, then you have like impedance mismatch between the two ports, and that leads to standing waves in this region. That's basically what we are observing. So without a droplet, you see the total RMS field is like constant. When you have a droplet in there, you have a standing wave. And then the standing wave, depending on how big the droplet is, you will have bigger patterns, like bigger responses. And why do you have so many of them? This is actually why the while the droplet is falling, this is the response. And why do you have it is because the droplet is falling to the more than antimodes of your standing wave pattern. So you have a very complex measurement over there, but you can use it to, like, for example, do one day profiling, right? Then you can take the peak and say, okay, that is related to the droplet diameter. Or you can take that's something else related, but you can use that information essentially to say what's rocket science or rocket billions. And this was actual measurement done with an additive system. So you can see everything else is that additive. We have a waveguide just over here. It's hard to see, but it's a very small waveguide. So with the droplet is falling and it kind of you see it falls in this bill. And these are actual real measurements of the waveguide for different type of droplets. So what's the bigger, like what's a simple thing that we can see? For a bigger droplet, you get a bigger response. For a smaller droplet, you get smaller response. Yeah. But you also get these kind of peaks and troughs. And you can see that the width of these troughs, the width of each of these standing wave pattern decreases as it falls through the part. And that is because of acceleration, because as the droplet falls, it kind of increases in speed, and you can see the differences in the peaks and clouds gets smaller and smaller. So we can not only get information about the size, but we can also get information about like how fast it's falling, speed, acceleration, and so on. Um, what was interesting is I don't have that slide over there. But if you have like different, like a bigger droplet, like one of those tadpole shaped droplets that I showed in the very beginning, you could have a droplet that actually covers a lot of the modes. So you would not have so many oscillations. So you can even say like the shape of the droplet. But the big challenge was the droplet had to fall through this T junction, which was the practical limitation. Because there is a big chance the droplet could actually stick to the sides of the waveguide. You're making it less non-invasive. You're making it more invasive, less non-destructive to be able to do it. So what we would ideally want is like a high-speed camera, right? It's looking at the droplet from a far distance. It's not hurting the processor. So can we just have a similar angle? That's why we replace this T junction with a waveguide. Very simple concept. It's just an open-ended waveguide that radiates fields out, and it's seeing the droplets in real time, in the near field. As you can see, these are more like 3D, 3D visualization. The droplet is in the near. The waveguide is in the near field of the droplet. We also have a high-speed good camera over there to make some correlations. But the goal is we will not have after we do the correlations. So these are the results with the waveguides. Uh, so this is the nozzle, this is the waveguide aperture, and the droplet is falling through the aperture. We can see a response, right? That's the first thing. We can see a response with the droplet, although it's subvaluable in terms of its size and the operating frequency. This is because we're operating in the near field. Okay. So we can see subwavelength phenomena. And then again, it's very similar correlations to the T-Hampton. Smaller droplet gives a smaller signal. You don't have so many peaks and troughs because there is no standing wave pattern over here. It's just coming in the field of view of the waveguide and then going out of the field of view. So you get that kind of a response. You can track you can track both the amplitude and the phase here. So you can get information, a little bit more information. And what we observed was the amplitude was more sensitive to the diameter of the droplet, and the phase was slightly sensitive to the distance between the waveguide and the droplet, which makes sense. So, like for example, what this distance is, which would kind of eventually say how the droplet is falling, like this or straight. So, amplitude directly related to size, phase related to like how far the droplet is from the waveguide. So what do we do with it? We did some preliminary like classification, trying to classify the droplets as like uh, high phase, low magnitude, uh, low phase, high magnitude, all those parameters, and try to like limit the cases and then do a physics-based optimization that basically predicts the droplet diameter and predicts the size, the distance with the actual cases, and then we get a pretty high conversion. It basically says that you can take a measurement, the diagnostic measurement, and then do physics-based optimization to invert for the droplet properties. But when we work with collaborators, you kind of train a neural network over here. It's a neural network with a regression model. So what a neural network, what it takes is basically and it predicts what the size, velocity, and the shape the droplet is. And then the neural network also takes in the output as well. And so it is a function of the input and the output, and the neural network part tries to predict what those weights of those functions are. And so these are five different phases, five different shapes, like a simple shape, an oblong shape. This is what we call as nut shape. This is a tadpole, and that's another complex shape. So five different shapes that we're able to consistently recreate. Because that's another challenge. How do we recreate? These are the five shapes with like fixed gas parameters or things like that that we were recreating. And then this is the classification. Exactly, this is what we call as the age index, actual versus prediction. If you have most of the stuff on the line, you can say you have a pretty good uh, 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 accuracy of prediction. So, just looking at the microwave signal, you can infer the shape of the droplet, you can infer the size of the droplet, you can also infer the angular position. So, that's, I think, kind of a major takeaway from this one. I don't know if I have time to go into this. I'm not going to talk about the movie Tenet, but it's why I give it is because it's a similar concept to what we do. Once we get like signals, the next step is how do you do some interesting full imaging with it, right? Because I guess most of you are aware of like ultrasound imaging and CT scan imaging and back propagation and so on. This is kind of similar where we use the concept of time reversal, which is kind of adopted from ultrasound, and and use it for TM. Here, what we see is two cars, one moving back in time and one moving forward in time, and they do meet at a time, right? If you move back from the past, if you move back from the future, and if you move forward in the past, if you meet at similar concept in time reversal, where they use forward propagation. So you can think of a source propagating out. You have say an array of antennas. You take this imaging antenna, uh, you take this measurement results, and then you just reverse it in time, and that will back propagate back to the source. This is the basic concept of time reversal used in a lot of different areas. And the big reason this work is because of the time invariance of the wave equation. This kind of starts falling apart once you have really lost materials. Because of the time causality is disrupted because you have a single derivative over it. But at the end of the day, we can do some approximation and we can still use this algorithm, this concept of time reversal focusing to images. Some really cool applications that I have used for it is number one is for detecting defects. So how does the algorithm work? You have a measurement, you take a measurement for a benign sample, then you take a measurement for the defective sample. Try to understand if you don't have a benign measurement, you can still extract out the defect response, backpropagate it in a numerical model, and use spatiotemporal localization to actually create hotspot energy images of your defects. Why defects? Because defects are secondary sources. So you need to take out this primary source, which is your you're transmitting antenna, or like if there's a big scatterer, and so on, and then you will get access to your defect information, use it to reconstruct. These are some reconstruction images of an impact damage. This was done back in my PhD, and this is an anti-labor mode where we are trying to see very thin cracks in a composite material. So this is an actual reconstruction result. I'm gonna be quick. So the next one is detonation imaging, and this is kind of similar to this is kind of something called direct labor mode, where we are trying to track a detonation front eating through a bunch of explosives. So it's a complex problem, but at the end of the day, the current way they use is microwave Doppler. Like you use a Doppler, like a similar Doppler shift concept, where you see once the target is moving towards you, you can see you can track the position and you can make a sense for where the connection front is. But still, like where you are in the Julie. Uh, sure, yes. But what's more interesting is the shape of that wavefront as well as it's propagating to the because that determines a lot of like, secondary phenomena. So this is actually a microwave imaging result. This is the true shape of the detonation front eating through the explosive. And this is the microwave image for the same concept. So you can clearly see that you can see the detonation front. For this we use antenna standard off. Trying to reconstruct. So that imaging is very computer. Yes. I'm using pulse microwave. Uh, the third is band. So this is I'm not gonna probably I don't have the time to go first question was that so that is airborne. That's ours. So that drone or something. Yeah, you can have a stand where you can place that. The cost is usual and the evidence. What's this? I love this. Uh, okay, so so I'm not gonna go into this topic because I don't have the time. But this is what I'm saying is at the end of the day, you can use this same time reversal concept to shape microwave energy in a very complex pattern. Like right now, here I'm trying to recreate the shape LLNL, which is my workplace shape here using the microwave antenna. What it basically says is you can use beamforming, microwave beamforming to focus energy at specific regions in a material, and then that material can react to electromagnetic waves. In that. So if you want to, for example, create a specific microwave pattern in a material, you can do that using same concept. Uh, so as you kind of move through the different sources, you can see your reconstruction event or beamform the energy getting more and more stronger. The final is like for Department of Energy project that we use is a very interesting application is project where we're trying to detect hidden wells. We're trying to detect wells, not hidden but orphaned wells. So wells that have been dug back during like 1800s, 1900, early 1900, and they're lost because nobody cared about them. And a lot of people plugged them. A lot of those wells were plugged, but a lot of the wells were not plugged. So these are essentially holes in the somewhere deep in somewhere beneath the foliage and whatnot. And this could be pretty harmful for different reasons because things that you put into the ground could actually leak that out from these wells. So there is a big effort going on to try to detect these orphan wells. And the biggest technique is magnetometer because magnetometers can basically detect metals. So you can just detect metals, but a lot of these wells did not have metal. Back in the day, a lot of those wood casing but they actually not have the metals because the metal was salvaged from one. So at the end of the day, we just have probably big pockets of chemicals in the ground, and we use the airborne ground connectivity data over here, combined with time towards the imaging condition for well interference. So that's another cool application of microwave imaging. Um, yeah, and then we also design some sensors that can do extremely high resolution imaging for micro. This is not using a reconstruction but actual like scanning, and these are mathematically inspired, so they can actually be really sub-wavelength in terms of its resolution characteristics. The application that is super cool, basically the image changed over here, but I actually am working on placing the sensors on wells. And these wells would be completely wireless. So these sensors would be wired looking at different regions of the wells for like corrosion or different fluids or damages in the cement casing interfaces, for example, and be able to interact with ground electronics to see how the well is doing in real time. So it's a very challenging problem to be able to monitor a well because of the harsh corrosive environment, because of no access to it, because it's plugged, once plugged, you really have to take off the head to be able to take some and diagnostic down the well. So if there are ways to monitor these wells in wireless reliable vision. So these are some preliminary results of actually actually, this picture is not going. Okay, so this was the dust sample, and this was actually a microwave scan of the dust, which did a very nice correlation of actually the extent of the dust and the microwave image. So, a lot of stuff that I covered, but hopefully I was able to make you all excited about electromagnetics. And and want to acknowledge again and also CNDE and everyone affiliated with CNDE to give me the opportunity to come here and present some of this research where most of the groundbreaking work is happening. And uh, also, back in the day, in 2015, I was at Professor Kavita's lab for about a few weeks trying to design antennas. Very this what year that was. Yeah, that's what 2015 you said. 2015. So it's great to be back. Thank you. Thank you. Six. All of PhD students and master students. Okay, it's a lab, but not not a lot of PhD students. Enough, enough to interact in my students. Okay, 10 to 12 more should be here. Why do you need a related? Expense of going. Expense of going. Expensive. Sir, I want to ask a basic question. You talked about volumetric radiology, right? How it is different to DLP, conventional DLP? Which works for a single layer. In DLP, you have I think digital like a light on that layer and that gets polymerized. Here you have a 3D projection. So you read from both 3D part. Okay, cool. So, yeah, that's it. is photopolymerized rays. You can also use resins in order ceramics because resins need to be photopolymers. So you will light that and that interacts with the solid things. So 3D imaging is transparent, optically transparent. And you don't have much optically transparent materials. For example, ceramics is not optically. That's why we are doing so that's conduct you will be dependent on multiple different workers because we or given levels. So with this technique, we should try to we always need a concept of sensors to monitor the velocity of yes, yeah. We're not targeting anything else. We're just trying to get big and chemicals. But we know that, like for example, force would also change the conductivity. It's, and so it becomes more complicated. So, but yeah, I mean, you can still use the overall technique to image defects as well as temperature. What you are reconstructing is conductivity, electrical conductivity. And electrical conductivity is just a function of everything, right? Force, temperature, whatnot. So ideally, when you get an image, you should get a representation of all those. But we have been keeping things simple and so just a front, a heat front, so that we are able to better understand the physics and move scale up from it. Yes. Commercial Olympic space, many systems. Those are not meant for temperature. Companies make products keeping in mind what their end goal is, which is like, for this case, they wanted a flexible sensor for to be placed in like metal geometry techniques. So they made the part optimized with keeping in sense for it, and not keeping in sense that you want to use it. So if you want to do that, then you have to kind of custom build your own sensor area or work with a company to like build that. So that's one of the limitations we observed is it was very hard to interpret the signal because of the low signal to noise ratio. You have to crank up the gain by like a lot of degrees to be able to see any meaningful information. So that's why you need custom solutions for your own customers. Thank you for sending us and sharing your experience. We are with us till like we would not be able to. If you want to interact, you can go into. Thank you. Thank you. Thank you for coming. Thank you. I'm really unhappy for our participation. It's recorded online. Yeah, we have recorded it. Actually, we wanted to make live because that's something it would not happen, but we can post it live. Still, I would like to see. We need to have a group meeting and